In this recording, we're going to talk about the characteristics of polynomial functions in factored form. A family of polynomial functions is a set of polynomial functions whose equations have the same degree and whose graphs have common characteristics. In this presentation, we'll talk about families that have the same x-intercepts. Now, suppose we have a polynomial function as shown here. F of x is equal to x minus 3 quantity squared times x minus 1. We can talk about the order of the polynomial function as a whole. In this case, the order of this polynomial function is 3. Or we can talk about the order of each factor of the polynomial function. The order of the factor x minus 3 is 2 because it's raised to the exponent 2. The order of the factor x minus 1 is 1. Sometimes you'll also see this written to say that the x-intercept at 3 is of order 2. And the x-intercept at 1 is of order 1. Okay? Now, we're going to look at a few functions as you see here. The upshot of what we're about to teach you is this. If you have an x-intercept with an even order, in other words, raised to an even exponent like all of these are, then what's going to happen is if the curve is above the x-axis, the curve will approach the x-axis at that x-intercept, touch the x-axis, and then bounce back up. If the curve is below the x-axis, heading into that x-intercept of even order, it will approach from below, it will touch the x-axis at that value, and then bounce down. So this is what happens whenever we have an even exponent on a particular factor, which creates an x-intercept. And the reason for that just goes back to what the parent function curves look like. Y equals x squared is a parabola that does exactly what I'm describing. It touches the x-axis and bounces back up. Y equals negative x squared does something analogous, but below the x-axis. It touches the x-axis and bounces down. The same is true for all these other functions that you see here. So we can generalize that behavior. If an x-intercept has an even order, then the intercept acts much like the vertex of a parabola. If the curve's below the x-axis to the left of the x-intercept, the curve will touch the x-axis at the relevant x value and then bounce down. If the curve is above the x-axis to the left of the x-intercept, then the curve will touch the x-axis at the relevant x value and then bounce up. So here are a couple examples. The first one, we've got the function y equals 2 times x plus 3 quantity squared times x minus 2. Now, this function here, the one I just put a red square around, if we looked at that fresh, we would say, okay, the lead term, if I was to expand that out, would be 2 times whatever the lead term is when I expand out x plus 3 quantity squared, which is x squared, times whatever the lead term is there, which is x. So I would look at that and I would say the lead term here is 2x to the exponent 3. So based on information in our previous slideshow, we would say that means that we have a positive leading coefficient with an odd degree. Now, whenever we have a positive leading coefficient with an odd degree in a polynomial function, we know that the end behavior is like this. Our end behaviors are in quadrant 1 and in quadrant 3. Okay, once we know the end behaviors, the second thing we do is then take a look at the intercepts. And we would say, okay, in this situation, we've got an x-intercept at negative 3, which is right here. And we've also got an x-intercept at positive 2, which is right here. Now, the x-intercept at -3, and then what we'll do is using those n behaviors and those x-intercepts, we'll read from left to right. So starting with the leftmost n behavior, which is down here, what we'll do is we'll approach that x-axis, but since it's an even degree, we know that we will bounce down. Okay, then we'll continue going left to right, but we'll see that we are approaching an x-intercept at x equals 2. This is a degree 1 x-intercept. So that means, just like a standard x-intercept, it just means that we're going to go through the x-axis, because there's nothing particularly special about an x-intercept of degree 1. We just cut through. And that's how we get what the function looks like. So we start by knowing what the n behaviors are, then we know what the x-intercepts are, then we make note ahead of time what will the behavior be like at those x-intercepts, and then we draw our curve. Similarly, what if we were given the polynomial function on the right? Well, looking at that, I would say my lead term will be -3 times x squared times x. So my lead term will be -3x cubed. That means I'll have a negative leading coefficient and a odd degree. So my n behaviors will be in quadrant 2 and in quadrant 4. Then reading left to right, I'll see that I have a x-intercept of order 2 at x equals -2 and an x-intercept of order 1 at x equals 3. Now, reading from left to right, I will approach the x-intercept of order 2 at x equals -2. Since it's order 2, I'll bounce off of it. And then I know that I have to cut back through the x-axis at x equals 3. And I'll make sure, since it's order 1, I just do just an easy cutting through of the x-axis. And I get a curve that looks like that. Now, what happens if we have an odd degree of a particular intercept? Well, if we have an intercept of degree 1, there's nothing particularly special about that. Those are easy to graph. We just go through the x-intercept at that x value. But what if we have an x-intercept of order 3 or order 5? To understand the behavior there, we'll take a look at the curve y equals x cubed, or y equals x to the 5, or y equals -x cubed, or y equals -x to the 5. What happens at those points is we get a point of inflection at the x-intercept. So for instance, if I was going to graph the curve y equals x minus 2 quantity cubed, what I would do first is I would say to myself, okay, I've got, if I expand this out, my lead term, the first term will be x cubed. That's got a positive leading coefficient and an odd degree. So I'll tell myself that what I'm going to do is have n behaviors in quadrant 1 and in quadrant 3. Then what I'll do is I'll say, okay, my only x-intercept is at x equals 2, but it's degree 3. Now, it can look kind of sloppy if you try to just draw this from left to right. So if you try to just draw like this, sometimes you don't really get a good idea of what happened. This is a bad job. Okay, you don't really get a good idea of the behavior around the intercept. What you want to do instead is find out, first of all, if you'll be, when you go from left to right, will you be approaching the x value of 2 from above or below? So let's focus our attention back on this graph. We say to ourselves, we've got a n behavior here and here. We've got an x-intercept at x equals 2. Reading from left to right, I see that I'll be approaching this x value of 2. When I come from the left, I'll be approaching from below. What I do to make a good graph is I first sketch the behavior of the curve near the asymptote, and I do it by starting on the x-axis itself and then drawing what the curve looks like going that way, and what the curve looks like going this way. And what I've now done is I've drawn myself a quality point of inflection. It's not a lazy point of inflection like this one over here is. It gives more of an idea that there's actually some interesting behavior going on there. Okay? So then, once I do that, I then can sketch the rest of my curve, and I get a curve that looks like that. So we have, when there is an odd a degree greater than 1 at a certain x-intercept, we draw a point of inflection. Okay? So when there's an odd order x-intercept greater than 1, suppose 3 or 5 or 7, etc., there's a point of inflection at that x-intercept. So let's quickly take a look at this curve right here. And we would say, okay, the lead term will be 2 times x cubed times x. So that's 2x to the 4. That means I've got an even degree and a positive leading coefficient. So my n behaviors will be in quadrant 2 and in quadrant 1. I'm going to now read from left to right and take into account the behaviors near my x-intercepts. One of my x-intercepts is at -3 and another one is at +4. I'm going to be approaching the x-intercept at -3. As I approach it from the left, I'll be above. So that means I go to that x-intercept, since it's going to be a point of inflection. I go to that x-intercept and I draw a quality looking curve, a quality looking point of inflection from there. Then I say to myself, okay, let's go from left to right now. Going left to right, I cut through that x value of -3. I approach an x value of 4, but since it's just a degree 1, there's nothing particularly special about that. I just make sure it's an x-intercept, I cut through it, and I go to the other side, and I've drawn a quality curve that respects the behavior near each x-intercept and has the correct end behavior. And if I drew it, if it had a negative lead coefficient, in other words, if I look at this curve right here, the lead coefficient would be -2x to the 4. My end behaviors would be in quadrant 3 and in quadrant 4. And then reading left to right, I would say my first x-intercept is at x equals -3. Since it's an intercept of degree 3, I want to make sure that I draw a quality point of inflection there. I'm coming at it from the left as I come from below, and now I can draw my curve. I go up a bit, but I realize I have to come back down because I have to get to my x-intercept at x equals 4. But that x-intercept at x equals 4 is just a degree 1 x-intercept. So nothing special, it just means go through the x-axis, and that now respects the end behavior it was supposed to respect by knowing the lead term. So like I've been saying, when there's an x-intercept of order 1, the function just passes nicely through. So looking at this polynomial function, if I was to expand that out, the lead term would be 2x cubed. Because it's an odd degree and a positive leading coefficient, I know my end behaviors are down here. I would then see that I've got intercepts at -4, +2, and +5. But each of those intercepts is not particularly interesting. They're all degree 1. So I just make sure that I draw a curve that goes through each of those intercepts. And that curve, if you do it correctly, will end up matching the end behaviors it's supposed to match. Now, the sketches done in the previous few slides illustrate the general idea, but to get marks on a test, pay attention to the level of care and detail used on graphs in the upcoming slides with photos from the graph paper. That's the standard you want to be working towards. So suppose I ask you to graph this function right here. Well, you don't have to expand out this polynomial. If you do, though, you see that the lead term would be 3x cubed. It's an odd order function with a positive leading coefficient. So I can determine that my end behaviors will look like that. I can then see that my intercepts will be at x equals -1 and x equals 2 and x equals 4. And each one of those intercepts is a degree 1 x-intercept. So there's nothing particularly interesting about them. So as I go from left to right, starting from below in quadrant 3, I see that I'm going to get a curve that looks sort of like this. Okay, and that's what we get. We don't know yet how high or how low to go. A lot of times curious students will say to me, sir, what's this point right here? How do we know that maximum or minimum point? You'll learn how to do that when you do calculus. Now, what if we're asked to sketch this curve right here? What's interesting about this curve is the fact that sometimes people forget you can have an intercept at x equals 0. So if we were to expand it out, we would see that our lead coefficient would be, lead term would be negative 2x to the 4. So our end behaviors are the end behaviors shown here. I would see that I have a x-intercept of order 1 at x equals 3, order 1 at x equals 0, order 1 at x equals 2, and order 1 at x equals 6. And, oops, you know what? I'm going to just change this for a second. I recall now, there's a little typo. Let's just pretend for a second that that said x minus 3. Okay, I'm just going to change the question. So if we see that that says x equals 3, that would actually make, ignore this one right here. That would make our x-intercept at x equals 3. Now, there's nothing particularly interesting about any of these x-intercepts, so we're just going to cut straight through. So starting from below, because that's what our end behavior tells us to do, and going from left to right, we see that we'll get a curve, and forgive me because this tablet's not the best for drawing on, we'll get a curve that looks something like this. Now, when you're using pen on paper, you can do a better job. Okay? And that's what the curve will end up looking like. And again, pretend, if you don't mind, the question said x minus 3, because when I drew the graph, that's what I made the graph of. Okay. Okay. Now, let's get into some more interesting types of curves. Suppose we wanted to graph the function y equals negative 3x times x minus 2 quantity cubed times x minus 5 quantity squared. Well, we don't have to expand out the function. We can see from this part that we've got negative 3x going into the lead term. We can see from this part that we've got x cubed going into the lead term. We can see from this part that we've got x squared going into the lead term. So the lead term is negative 3x to the 6. Because the lead term is negative 3x to the 6, we can see exactly what our end behavior should be. Now, we know that we've got intercepts at x equals 0, at x equals 2, and at x equals 5. And here's where a little planning goes a long way. We know our end behaviors are below and below. And so we know that as we approach this x-intercept at 0, we're going to be below it and we're going to be going above. But then, as we know we have to still approach this x-intercept at x equals 2, what sometimes students do, and it's not the best thing, is they just sort of try to do it all from left to right. And when they do that, they don't do a great job at that point of inflection of really showing what's going on. Instead, what you want to do, instead of doing that, is you want to do what we've shown in blue. Ignore the red at x equals 2 for a moment and look at blue. We know that we have a point of inflection, and we know as we approach from the left, we'll be above because we thought forward a little bit. So let's draw a point of inflection that goes that way, and that's what's shown in blue. So what we're now going to do is we're going to draw that before we draw the curve. Then we're going to make a curve fit that. It's easier to make a curve fit that than it is to fit a point of inflection into a curve that you're trying to draw. Draw the point of inflection first, then draw the curve. And when you do that, you end up with a good-looking point of inflection at x equals 2. And as we saw in that last slide, we know as we cut through x equals 2 that now we're going to be approaching x equals 5 from below. So we already kind of know what that, we already know that that x-intercept is going to look like the vertex of a parabola, sort of, and we can make a curve like that. So I guess what I'm trying to say is respect what it's supposed to look like at those x-intercepts, because you'll be marked on that. We don't know how high or low to go between x-intercepts. We'll learn that in calculus when we learn derivatives. Now, what if we wanted to sketch this curve? Well, first thing we want to do is determine our end behaviors. We've got a negative lead coefficient with odd degree, so our end behaviors are shown in blue. We're going to common factor out negative x cubed, and when we do that, we have x squared minus 4 remaining, which gives us x minus 2, x plus 2. That tells me that I've got a intercept at x equals negative 2, an intercept at 0, and an intercept at 2. I'm going to be approaching this first x-intercept at x equals negative 2 from above. So I'm going to be going through like this. Now, rather than continue from left to right, I'll go to my next x-intercept, which I know is at x equals 0 and is a third degree, so it'll look like a point of inflection. So I'll draw my point of inflection first. Then I'll draw my curve to fit that point of inflection. Then, coming out of that point of inflection, I see that my x-intercept at x equals positive 2 is degree 1. So there's just a degree 1 x-intercept there, so that's pretty easy to draw. And I'll get a curve that looks something like that. And there we go. Okay? We don't know how high or low to go. We'll learn that in calculus. Now, suppose you're told that you have a polynomial function of order 6 with an x-intercept at x equals 2, an x-intercept of order 3 at x equals 0, and an x-intercept of order 2 at x equals 1. The curve passes through 112. You want to know the equation of the function. So right away, you know, I've got an x-intercept at x equals 2. I've got an x-intercept at x equals 0. And that's of order 3. And I've got an x-intercept at x equals negative 1, and that's of order 2. Now, you might be saying, well, how do you know what the exponent is on x equals 2? Well, since it's order 6, we know that the degrees of the x-intercepts can't exceed 6, so this must be a 1. Because 1 plus 3 plus 2 is equal to 6. It couldn't be on x equals 2, on the x minus 2 factor, we couldn't have an exponent of, say, 2, because 2 plus 3 plus 2 would be 7, and that can't exceed 6. So we know that our function is going to look something like this. Now, naturally, it's just a convention. We typically put the x cubed first because if one of the factors is x minus 0 and we just show it as x, we typically put that one before the other x factors. And finally, something like we learned in grade 10 is we should put an a here because we don't know exactly what the vertical stretch factor will be. So what we can do is say that we've got a polynomial in the form y equals ax cubed, x plus 1 quantity squared, x minus 2. Okay, so now we also know it goes through 112. Well, we're going to let x equal 1 and y equal 12, and that's going to help us solve for a. So when we let x equal 1 and y equal 12, we end up with 12 equaling negative 4a, which means negative 3 equals a. And so the equation of the curve that's being described is y equals negative 3x cubed times x plus 1 quantity squared times x minus 2. This question here asks us to determine the equation of this 7th degree polynomial. Well, when you look at this, first thing you might say is, okay, we're going to put an a here. I know I've got an intercept at x equals negative 3. And I know I've got an intercept at x equals negative 1, and an intercept at x minus 2, and an intercept at x minus 4. Now, I can tell that the x equals 2 and x equals 4x intercepts are both degree 1. But I don't know what the degree of the x equals negative 1 x-intercept is, because that could be degree 2 or it could be degree 4. And similarly, I don't know what it is here, because that could be degree 3 or it could be degree 5. Okay? So, or degree 7 or degree 9, and this could be 2 or 4 or 6 or 8. You get the idea. All we know by looking when we see that point of inflection is that it's an odd degree, and all we know greater than 1. And all we know by looking when we see that, that what looks like the vertex of a parabola on x equals negative 1 is that it must be an even degree. Well, keep in mind that it's a 7th degree polynomial. And so there's the only way that we could have the exponents on the x-intercept factors not exceed that 7 is if we have a 1 at x equals 4, a 1 at x equals 2, a 2 at x equals negative 1, because that's one of our options, and a 3 at x equals negative 3, because that's one of our options. If we put those exponents up, we get 3 plus 2 plus 1 plus 1, which equals 7. And that's a possibility for our factor. So in other words, what we're saying is the exponents must be the ones I've just shown up at the top. If I tried to put a 5 here, if I said, okay, I'm going to put a 5 there because it's a point of inflection at x equals negative 3, so therefore it might be degree 5. On one hand, that might be right, but on the other hand, if you now add the factors, if you now add the orders of those intercepts, you would get 9, and we're not allowed to exceed 7. Okay, I'm not going to be trying to trick you on things like that. It's just something I wanted to point out to teach you. Okay, so what we're going to be able to say as we go through the explanation of that, like it says here, we've accounted for order 1 at x equals 2 and order 1 at x equals 4. So we've accounted for 2 of the 7, 5 remaining spread among the x-intercept at x equals negative 3 and x equals 1. So this must be degree 3 and this must be degree 2. Again, that's me just repeating what was said earlier. So what we get is the function y equals a times x plus 3 quantity squared, x plus 3 quantity cubed times x plus 1 quantity squared times x minus 2 times x minus 4. Now we're going to plug in the point 0, 54 because the y-intercept is 54, and when the y-intercept is 54, that means we go through the point 0, 54. Plugging in a 54 for y and a 0 for x, we get 54 is equal to 216a, which means a is equal to a quarter. So our function is therefore y equals 1/4 times x plus 3 quantity cubed times x plus 1 quantity squared times x minus 2 times x minus 4. And that's the end of that slideshow.